Hello, this is Math Jazz from Almost Cool. I am doing my calculus live stream right now, and I have some questions ready to answer, and I also have my email and Facebook up so that you can send me questions that you may not have been able to get to me before we started recording. So feel free to send your questions to me. Wait, let me, there we go. So, our first problem is going to be problem 1. Give the partial fraction decomposition of 2x divided by x squared minus 1. The way to do this, well, first we have to factor the denominator of this expression. So, I will factor it, and then I need to set up a generalized sum of fractions that is going to equal our original fraction. So I have here the factors are x plus 1 and x minus 1. I've set up a over x plus 1 and b over x minus 1. So this sum of fractions here should be equal to our original fraction when we're done with this process. So after I set up this fraction is equal to our generalized sum of fractions, then I'm going to multiply by the denominator on both sides of this equation, and that'll give us 2x on this side because the denominator will cancel. And then we'll get an incomplete cancellation on each of these other fractions. So the x plus 1 term cancels on the a, leaving just a times x minus 1. And likewise, we have b times x plus 1 because the x minus 1 canceled with the denominator of this second fraction. So that's our first step. And we're going to just call this setting up the problem from now on. And we'll kind of gloss over a little bit how to do this. The first step is to set up this particular equation in this particular way. After we do this, we want to solve for a and b. And we can see that if we plug in particular values for x, we can kill off several variables at once. X, of course, will become a constant, and if we pick x as 1, then we get x minus 1 is 0, which means that the a drops out too because a times 0 is 0. So we're going to set x equal to 1 and solve for b. So we get 2 times 1 on this side of the equation is 2. As I said before, the a term cancels out. And then this b term becomes b times 1 plus 1, so b times 2. So 2 equals 2b, which means that b equals 1. We can do the same technique plugging in x equals negative 1 to solve for a. So again, the negative 1 kills off this factor, and therefore this whole b term dies. We have a times negative 1 minus 1 is a times negative 2. And on the other side, we have 2 times negative 1, which is negative 2. So that's how we got this equation here after plugging in that value of x. And solving for a gives us that a also equals 1. The final step of the problem is to take these two coefficients and plug them into our generalized sum of fractions, which is this sum up here. So we get solution. We plug a and b into the generalized sum of fractions, and we get that 2x divided by x squared minus 1 is equal to 1 over x plus 1 plus 1 over x minus 1. So that's our first problem. Problem 2 is also a partial fraction decomposition. So the first thing we have to do is we have to set up the problem. like so. This is a little bit of a special problem, though. Notice that when we factor the denominator, we get that this is x minus 1 squared. Now, when we set up our generalized sum of fractions, we're going to have to represent both x minus 1 and x minus 1 squared as denominators in our fractions in our sum. So I have here a over x minus 1 and b over x minus 1 squared. And this will be our proper form for our generalized sum. If we had had x minus 1 cubed as a factor of the denominator, we would have an x minus 1 fraction, an x minus 1 squared fraction, and an x minus 1 cubed fraction. Basically, we have to represent every power up to the highest power that occurs in the denominator of our original fraction. So, after we do this, we have to kill the denominator on each side. The same way that we did before, we end up with x plus 4 equals a times x minus 1 plus b. Because, of course, when we multiply by this denominator, that turns out to be x minus 1 squared, which completely kills this denominator, leaving b all by itself. Now we plug in x is 1 to kill off the a term, and we get 5 on this side of the equation, and b on that side of the equation. The a term dies. So b equals 5. We plug b into this equation, and we pick a value for x. I'm going to pick 2 because 2 minus 1 is 1, which is really convenient. So by plugging in our b value and letting x equal 2, we end up with this equation. Actually, we don't. We end up with 6 on this side. I have a typo. That can be fixed. So there's 6 on this side. 6 equals a plus 5. So a equals 1. Let's see, solution 24, 23. So we need to plug a and b into our generalized sum of fractions. A is positive 1, so I'll fix this. So we have that our original fraction equals 5 over x minus 1 squared plus 1 over x minus 1. And it's time to find another partial fraction to decompose. Or I guess it's a fraction to decompose into partial fractions. Anyway, here is problem 3. Give the partial fraction decomposition of 8 over x minus 2 squared times x plus 2 squared. Now, with this, we have two terms that have powers greater than 1. So that means that we're going to have to represent I need to kill off this cell. There we go. So we have two fractions with powers greater than 1, two factors in the denominator of the fraction that have powers greater than 1, and each of those needs to be represented in every power up to the power that's present in the denominator. That is, we have to have an x minus 2 and an x minus 2 squared, and we have to have an x plus 2 and an x plus 2 squared. Get rid of that one. And get rid of that one. The commands should have cleared the screen before putting up the problem. So I'll try and fix that for next time. Anyway, so solution to 3, part 1. We set up the problem. Now notice, exactly as I said, we need to have a first power of x plus 2 and a second power, and a first power of x minus 2 and a second power. And we need to have a brand new general coefficient on each of these, a brand new variable on each of those. And then we're going to multiply on both sides by the denominator, and we end up with this, which is very long. However, we do notice that if we plugged in 2, this would be 0, so this whole thing would be 0, and this would be 0, so this whole thing would be 0, and this would be 0, so this whole term would be 0, and all we're left with is d times some number is equal to 8. So that's what we're going to do. We're going to let x equal 2 and go from there. Same thing for x equaling negative 2. If we have x is negative 2, that dies, so the a term dies, and this dies, so the c term dies, and the d term also dies. So all we're left with will be b. So when we plug in negative 2, we get 8 equals negative 2 minus 2 is 4, squared is positive 16. Sorry, negative 2 minus 2 is negative 4, squared is positive 16. So we get 8 equals 16b, and we solve, we get b as a half. Same thing over here, 2 plus 2 is 4, squared is 16, and then, so we get 8 equals 16d, d equals a half. So this is the part where we plugged in. These two lines are the lines where we plugged in negative 2. These two lines are the lines where we plugged in positive 2. And we were able to solve for b and d respectively. Now with that information, we can try finding a and c. We're going to have to pick other values for x. We can't reuse a value. So since we already used negative 2 and positive 2, we can't use those again. They don't give us any new information because they've already given us all the information they can. But plugging in our values for b and d and letting x equal negative 1 and x equal positive 1, we'll end up with these equations. 3 equals 9a minus 3c, and 3 equals 3a minus 9c. So we can see that if we plugged in 1, we'd get 1 plus 2 is 3, and then 1 minus 2 is negative 1, squared is positive 1, 1 times 3 is 3, 3 times a. So plugging in 1 will give us this equation, and plugging in negative 1 is going to end up giving us this equation. From here, we're going to do elimination to be able to find values for a and c. So I decided to multiply this equation by 3 and subtract it from the first equation. So this is the second equation multiplied by 3. 3 minus 9 is negative 6. 9a plus 27, 9a minus 9a. Mathematica doesn't like putting negative numbers in front when it can avoid it. So 9a minus 9a is 0. And then negative 3c plus 27c is 24c. Solving for c gives us c is negative 1/4. We plug this value of c into any one of our previous equations with a and c. It looks like I chose this one. So we plug c into that equation and we get this equation. And then we subtract 9/4 from both sides. 3 is of course 12/4. 12/4 minus 9/4 is 3/4. Divide both sides by 3, we get a is 1/4. And now that we know a, b, c, and d, we can plug all of these values into our generalized sum and get that our original fraction, which is here, is equal to these four fractions added together. Problem 4. Give the partial fraction decomposition of x plus 6 divided by x minus 2 times x squared plus x plus 2. So, we set up the problem. Now this one is also a little special. We have here an irreducible quadratic. When we have these, the numerator can't be a single variable. It has to be a line with a variable for its slope and a variable for its constant. So this is how we have to set up this problem. Now, some of you are going to say, but we can factor this quadratic with imaginary numbers. And that is completely correct. We can. But we're not going to for this. What happens if you factor it with imaginary numbers is you'll get 3 linear terms. Here's one of them. And then this will factor into 2 linear terms. And you'll have a over one linear term plus b over another linear term plus c over the last linear term. And it'll use the same techniques that we've done before. And it's not so bad. However, this by not factoring this, I can show you how to do a problem where you don't factor. That's a tautology, but that's true. I mean, it's a different technique when if you're not going to completely factor to linear terms, to linear factors, you're going to have to use something besides a constant on the numerator of your fraction. So this is how you handle that. And in general, if you didn't want to factor a cubic, you would have to put a quadratic up here. Ax squared plus bx plus c. Or if you had instead of having a quadratic base, if you had a base that was to the 4th power, you'd need a numerator to the 3rd power where every term had a variable coefficient. But no one does that. The only things you'll ever see are going to be linear denominators with constant numerators, or quadratic denominators with linear numerators. Okay, or yeah. So the benefit to this is that it'll give you real values for all of your coefficients. You won't have any imaginary or complex values. Whereas, as I said before, this factors in complex field. You can factor this with complex roots. If you did that, you could split into 3 fractions instead of 2, all having constants in their numerators, but you're no longer guaranteed to have only real numbers. You might have complex numbers, you might have imaginary numbers. So that's why you would do this instead of factoring completely using imaginary numbers. Sometimes you don't want to use imaginary numbers. So that was a digression, but I think that was an important discussion also. So, going from there, we multiply by the denominator, and we end up with, this is our expression, 6 plus x equals a times x squared plus x plus 2, plus x minus 2 times bx plus c. This is solution 4.2? Yes. So if we plug in x is 2, then this term becomes 0, which means that this becomes 0. This, of course, becomes 2 squared plus 2 plus 2, which is 8, and this side becomes 8 as well. So 8 equals 8a, so a equals 1. Now, we're left with, when we plug in a as 1 into this expression, we still have two unknowns, b and c. And to get them, we need to have two equations. You can't find values for two variables unless you have at least two equations. So, we have to pick values of x to generate two equations, and we can't use values of x we've already used. So x equals 2 is out of the question. But 1 and 3 tend to be, 1 and 3 seem to be nice values for this particular example. Sometimes you'll have to think a little bit to figure out what number you want to use, but in this case, 1 and 3 seem to be particularly nice because, for example, we'll get 1 plus 1 plus 2 is 4 here, and we'll get 1 minus 2 is negative 1 here. And so that's pretty nice. We'll get 7 minus 4 is 3, and over here we'll have negative bx and x is 1, so that'll be negative b and negative c. So that's how we got the first equation. We plugged 1 in. Plugging 3 in gives us the second equation here. And then we can use elimination to solve for b. I think this will be solution 44. Yes, so we add the two equations together to solve for b. We get 2b is equal to negative 2. So b is equal to negative 1. And then we plug this into any of our previous equations. I chose this one. Plugging negative 1 in for b gives us that c has to equal 2. C has to equal negative 2. And now we know a, b, and c, so we just have to plug those into our generalized fraction sum. So that's going to be solution 4 or 5, I think. Yes. And so we have that this fraction here is equal to the sum of these two fractions. On to question number 5. Let me clear the page. Oh, that doesn't work as effectively as I would have liked. I'll clear the page manually. Problem 5. We're switching over now to linearization. This is in response to a question that was received on my email account. So I am listening and I do answer your questions. So this question was, I'd like to request a video in which you explain the similarities and differences between linear approximation and Newton's method and the setup. So this is going to be kind of a stopgap, if you will. I'm going to talk about using linearization and Newton's method in this video and do a few examples, and then I will be working on a more formal video to put up in the next maybe few days or a week. So this is some examples of how to use linearization, and we'll do the same approximations using both linearization and using Newton's method, and we'll show how they're different when you set them up. And I'll have a video on exactly this topic in the near future. So, solution, let's see, 5.1. So, to set up the problem for linearization, we're trying to get the output of the function to be the value that we're looking for. In Newton's method, you always set up your function so that a root of your function is the answer to your problem. But for linearization, you're going to set it up so the y value of your function is the solution to your problem. So that's why if I want to approximate the square root of 17, what I want is something where I plug in 17 and I get out the square root. With Newton's method, we want something where when I plug in the square root, I get out 0. And we'll talk more about Newton's method later, but here's how we do the problem with linearization. So the first thing is, of course, to pick the right function. We're looking for a square root, so we use the square root function. We want the square root of 17, so we pick the closest number to 17 that has a nice square root, 16, and we let that be the point where we linearize. So this is 5, 2. So we need to take a derivative, and we need to plug a into the derivative and into the function. So the derivative is here, 1 over 2 times the square root of x. And f of a is 4, so f of 16 is 4. And f prime of a is 1 over 2 times 4, which is 1 over 8. From here, we're going to find the tangent line. So I'm using slope-intercept form, I'm using point-slope form and then converting it into slope-intercept form. So I have y minus 4 equals 1 over 8 times x minus 16. I solve for y. I have this. I plug in 17 because I want the square root of 17. And I get out y equals 33/8. I am going to find the decimal version of this, which I guess is going to be somewhere around like 4.125, but I think that's it. But I don't do mental math as well anymore. Yes, 4.125. I did get it. That's great. So 4.125 is our approximation of the square root using linearization. But we're going to do the same thing. I'm not even going to clear the page. I'm just going to keep going so that we can have this on the screen when we look at when we're done with Newton's method. We can compare the two. So problem 6. Use Newton's method to approximate the square root of 17. So as we said before, with linearization, we want the output of our function to be the value we're approximating. So the function is the square root. The output of the square root function is square root of 17. For Newton's method, we want the input of the function to be square root of 17. Like when we plug in square root 17, we should get out 0. And that's going to be how Newton's method will differ. It's the opposite. The y values were the approximating, the y variable was the approximating variable in linearization, but the x variable is the approximating variable in Newton's method. So, solution 61. We set up the problem. Notice that with this problem, if I plug in, where's my cursor? If I plug in the square root of 17 for x, I get out 0. That's how Newton's method works, is that the value we're looking for is the one that makes the function 0. As opposed to here, where the value that comes out is the value we're looking for. I think Newton's method is sometimes a little more abstract, a little bit harder to understand at first. Anyway, so we are going to... That's fascinating. I think I skipped a step. 60. This is 61. This is 62. Huh. Okay. So the steps that got omitted, I'll do them here, and then we'll catch up to where we were. So we have to, once we've set up our problem, we have this f of x, we need to find its derivative. So that'll be f prime of x is equal to 2x. And we need to have a guess. So our initial guess will be a is equal to 4. We should make a pretty good effort to get a good guess, but we also don't need to overdo it. Better guesses mean that we don't have to iterate Newton's method as many times to become confident with our example, or confident with our answer. But also, most of the time, when you pick a number, it'll converge pretty, especially for questions that are asked on exams. You'll get numbers that converge pretty quickly. And, if you're really worrying about getting good guesses and having quick convergence to the answer, then there are computer science books that tell you how to do really nice approximations. But doing Newton's method by hand is usually, it's something that we do on exams. It's not something that you do in real life. Anyway, so we make our guess. We pick a as 4 because we know the square root of 16 is 4, and 16 is close to 17, so 4 is a pretty good guess to start off with. And that's how we start. Oh. So now that we have our first guess, I guess let's call this x sub 0. There we go. There we go. So our first guess, x sub 0, is going to be 4. We have our function, and we have our derivative. And so we plug them into our algorithm. So to get our first guess, to get the x sub 1 guess, we plug in x sub 0, f of x sub 0, and f prime of x sub 0. So we're going to get, here we're going to get f of 4 is going to be 4 squared, 16, minus 17 is negative 1. Negative, well, yeah, the negative and the negative. So 16 minus 17 is negative 1. This negative sign cancels with that, so we get a positive. And then 4 into the derivative gives us 8, so we have 4 plus 1 over 8, which is what our first approximation is here. It was 4.125. So our x sub 1 in our Newton's method gave us the same answer as our linearization method did. But the benefit to Newton's method is we can now use this approximation to hopefully get a better approximation. So let's see that. So we're using this same equation. There's my cursor. We're using this equation. If we want x sub 2, so our second approximation, we plug in our first approximation, x1, and we have f of x1 and f prime of x1. And if we did that, we get out this number. If we do it again, we get out this number. And after that, the differences between our values become too small to show. Well, you can tweak the settings of Mathematica and force it to show some things, but the difference is, I guess, less than 1, 2, 3, 4, 5, 6, 7, 8. The difference is going to be further than 8 decimal points beyond, or decimal places beyond the decimal point. So it doesn't matter after that. So what I mean by repeat algorithm until conditions are met is when you're doing one of these problems, you might be asked to repeat the procedure until you get the first so many digits correct. Usually like the first 3 digits correct or the first 4 digits correct. Or you might be asked to, you might be given a certain starting number. So you might be given a set x0 instead of being asked to pick one on your own, and just be asked to repeat the algorithm 3 times or something like that. So it's so this until conditions are met is very vague and depends on what you're trying to do. If you're trying to design something and you're using Newton's method to approximate something, usually you'll do that by computer, but you would be more concerned with, I want to get so many digits of precision in my calculation so that my measurements can be correct on whatever I'm doing. But if you're doing an exam, it might be, and this is less realistic, less what you'd do out in the real world using math to solve a problem, but on an exam you might be asked to just do it so many number of times, and that would be the condition for that particular scenario. So until conditions are met are context-based. Well, those are the problems that I had so far. But we can do some more Newton's method and more linearization problems to fill out the last of the hour. So let's do another one of these. So instead of approximating the square root of 17, let's approximate the square root of 8. So approximate the square root of 8. And we're going to do this using both Newton's method and linearization. So, in Newton's method, we want the square root of 8 to be the number that makes our function become 0, the number that kills our function. So, we're going to let f of x be x squared minus 17. Sorry, minus 8. Also, notice how if I plug in square root of 8, I get square root of 8 squared is 8. 8 minus 8 is 0. So that works. That's what we want. So that means that our derivative is going to be f prime of x is equal to 2x. Same as before. And our guess, so our x sub 0 is going to be, well, 9 is close to 8, and the square root of 9 is 3. That's pretty nice. So we're going to let our our first guess be 3. So that's our first step in this problem. And then we're going to remember our formula, which is going to be x sub n plus 1 is equal to x sub n minus f of x sub n. Oh no, I did not want an inline cell there. There we go. F of n divided by f prime of x sub n. There we go. So we want this to be our function. Or sorry, our whoa, that disappeared entirely. There we go. So we have our formula. We're just going to plug these numbers into it. So we get 3, well, let's give this a name. So x sub 1, Mathematica doesn't really like subscripts, unfortunately. X sub 1 is equal to x sub 0 minus f of x sub 0 minus, so that's 3 squared minus 8, that's f of x sub 0, so f of 3. And then we want to divide that by f prime of 3, so that's going to be 2 times 3 is 6. And we get 17 over 6 as our answer. And then we can do this again. Actually, let's get a decimal. So 2.83 repeating. And then to get the next number, so x sub 2 is equal to n times x sub 1 minus, actually let's define some functions here. So f of x is equal to x squared minus 8 and f derivative. That'll be good enough for a derivative. There we go. So our second approximation is equal to our first approximation minus our function with our first approximation plugged into it divided by our derivative with our first approximation plugged into it. So this is our second approximation, 2.82843. And since the way this is written, it says take your current approximation, plug it into Newton's method, and then put it in the same place in memory where your approximation was. So if I just keep hitting enter on this line, it'll keep giving me the next approximation and the approximation after that and so on. So that's kind of cool. So this is our first approximation, this is our second approximation, and here's the third and the fourth, and it looks like it's already stabilized. Maybe if we give it a few more decimal places. Let's make it go out to 15. Huh. It's weird. Doesn't want to go any further. I think that's the command for more precision, is n comma some number. Anyway, so I have this approximation. Let's see how close we get to having the correct square root. So the square root of 8 is what we're looking for. That's Mathematica being silly. There we go. Hey, look. It actually matches for at least the first, I guess, 5 decimal places. I wonder what happens if we force it to subtract a. I'm betting that there are digits that are off further down the line that Mathematica is just not giving to me. Anyway, so that's how to do this using Newton's method. We get our approximation a. Let's delete all of the extra stuff. Our approximation is 2.82843. Now if we were to do this using linearization, we would have to pick a function. We'd pick the square root function, so we'd get f of x is equal to the square root of x. And then we get the, our guess would be a is equal to, well, our guess would still be 3, because that's still the, well, sorry, a will be 9, because that's the x value that's closest to 8 that we can take a square root of easily. So, whereas in Newton's method we picked our guess to be as close to the answer as we could get. That is, we knew the square root of 8 was somewhere near 3, so we picked our guess to be near 3. With linearization, we have to do it the other way around. Instead of saying, where do we think the square root of 8 is, we say, what number near 8 is easy to take the square root for? And so we pick 9. So it's a little bit different already. Like, we already, I guess we already had to pick a different function, but we also have to pick a different starting point. So we have these as our, I assigned a value to A. Let's use B. B should be open. Okay. So here's our linearization method. There we go. Oh no, we already killed it. Okay. Let's put those back up again. Math form. We want our function to be the square root function. We want A to be, we're going to use B because we've already written on A. So A is going to be the value 9, or B is going to be the value 9. Okay, so with linearization, we have set up our, oh, we already used F. There we go. Oh, we might as well do that too. So we've picked our function, and we've picked the point where we're going to approximate from, the point where we're going to linearize. We find the tangent line to F at A, so that means we're going to have to use the derivative. Let's find the derivative. F prime of x is equal to 1 over 2 times the square root of x. And so we get our line. So our line is going to be y minus 3, because when we plug a into f, we get 3. So that's the y value of our point. And then we're going to have an x minus 9. And then we have to figure out what the slope is. Well, the slope, when we plug in a, we get 1 over 2 times the square root of a, so that's 1 over 2 times 3, so that's 1 over 6. So our slope is going to be 1/6. So I'll just divide by 6. And this is our line. And if we just add 3 to both sides, we solve for y, like so. From here, we just plug in 8. So let's get a math form going. We plug in 8 for x, and Mathematica is not going to put that in a decimal right away, so we're going to have to force it to do that. And we get 2.83 repeating, which was, if you remember, the first approximation we got from Newton's method. And that actually tends to happen a lot. I'm not sure if Newton's method and linearization always give the same answer, because I haven't thought about it much until right now. But I feel it's safe to say that for square roots, the linear approximation will be the first order Newton approximation. So x sub 1 and linearization should be the same number, at least for taking square roots. And maybe when I do the video on this, I'll look into this more and see if I can strengthen that claim. Maybe prove it, or maybe it's true that the linear approximation is always the Newton approximation, which would be pretty cool to know. I know I don't know it right now, one way or the other, but that would be pretty cool if it were true. Anyway, so this was today's live stream. I hope that you all are enjoying learning calculus. I am grateful to the question that I received or the person who sent the question to me in the to my email address. That was really cool. And thanks for watching.